Hi students, in this video we're going to look at how to use integration techniques to estimate the area under a curve. Alright, so after watching this video you should be able to examine the area problem and then use this very wonderful looking formula to estimate the area underneath basically underneath the curve or the graph of some function. Biggest thing you have to remember is how to find the area of a rectangle. So remember, length times width. Got that? And the rest of this video should largely, hopefully, be okay. Alright, so we've got this area, we've got this graph shown to the right. And we want to basically think about how can we work out the shaded area underneath that curve. Right? That's what we call the area problem. How do we find the area underneath this curve? The trick is there aren't any nice, neat geometric shapes there. We don't have rectangles or circles, even anything like an ellipse. It's this curve that has no neat way to help us find the area underneath it. So how could we find the area underneath? Now, the simplest thing we could do is use some rectangles. So let's say we start down here. We might draw a rectangle here, and then another rectangle here, and then another rectangle here, and so on. Whoops. And we could just keep adding in rectangles underneath that curve. And then if we add up all those rectangles, we might not get the exact area underneath of that shaded area underneath the curve, but we'll get something close. We'll get something that gives us a ballpark range, a ballpark figure for that shaded area, for that area under the curve. And using rectangles is nice and simple, right? It's length times width. We can just work out those values very easily. So we can find, or at least we can estimate, the area underneath the curve by drawing in these rectangles and adding in the area of each of those rectangles underneath the curve. Now, how do we find the area of those rectangles? Well, looking at this middle rectangle, for example, we need to know the width and we need to know the height. Now, what is the width of this rectangle? We can work it out pretty easily. But what is the height of that rectangle? Well, this curve is y equals x squared. So if we want to find out the height of this rectangle, well, we just need to substitute in a value of 2 into our function. So the height is going to equal, well, x value is 2, so the height is going to be 2 squared. The height of our graph is equal to whatever the value is of our function. Right. And then we're going to, so we find out the value of our function, substitute the number in, and then multiply that by the width of our rectangles. That gives us the area, and then we do that multiple times. We can add up those areas, get our answer. And that's what this formula is basically giving us. So A is for area, and it's an approximation, right? This isn't going to give us the exact area. It'll give us something in the ballpark. Is equal to this sigma here. That sigma means sum. So the sum of, and this part here really just means the area of the rectangles, because basically this formula is length times width. This back form is the width of our rectangle. This part here, f of xi, is the height of our rectangles, of each of our rectangles. So what we're doing with this formula is summing length times width, or height times width, however you want to think about it. We're finding our areas of each rectangle, determining the height of the function, times by the width, and adding them all together. Alright, let's do an example. Let's estimate the area underneath our curve here, y equals x squared on the interval 0 to 5, using 5 rectangles. Well, we could start off with by working out the width. So the width, sometimes we call it lowercase delta x. Well, our width in this case, we're going from 5 to 0, so we're covering a distance of 5. we're using 5 rectangles, the width of each rectangle is going to be 1. Like, we could just look at that and see it, but we could use something like this to help us work out how wide our rectangle should be. Now, the next part we have to do is work out the height of each rectangle. So let's go with rectangle 1. We'll just number these. We'll go 1, 2, 3, 4, and 5. So rectangle 1, the area is going to be the function at 0 times by our width, which is 1. Now, the function is x squared. Okay, so it'll be x, so that'll be 0 squared times 1, which equals 0. And that makes sense. There's no rectangle there for rectangle 1. Then for area 2, that'll be my function at 1 times by my width, which is 1. 1 squared times 1. That rectangle has an area of 1. And then continuing on, 3 is my function at 2 times 1, which is 2 squared times 1, which is 4. Area 4 is going to be f of 3 times 1, which is 3 squared times 1, which is 9. Area 5 is going to be f of 4 times 1, which equals 4 squared times 1, which equals 16. So my area is going to be approximately equal to the sum of all these values, 0 plus 1 plus 4 plus 9 plus 16 equals, I think that's 30. So the area under the curve here is approximately 30, you could say 30 square units, but it looks like it's about 30. Now the thing is, we've talked about this being an approximation, and it's pretty easy to see why. We found the area of all these rectangles and added them all together, but we're missing these large looking gaps in between. So we're missing some quite significant areas in here with our estimation. So the question then becomes, well, how could we make our estimation better? Have a think, and when you're ready, you can pause the video and have a think. We'll go through it on our next slide. Now, we could make our estimation better by just including more rectangles. Notice with this, we've got our first example here with these big gaps of areas that we didn't really count in our estimation. If we increase the number of columns, or the number of rectangles we use, like in this second one, we've got much smaller areas that we have missed. So this estimation from this graph will be much better. Over here on the far right, these rectangles are so thin, and those gaps are so small we can barely even notice them. So if we increase the number of rectangles, if we make the width of each rectangle smaller, we will be able to get a much better estimation than if we use only a few rectangles like we did here. Now the downside to that is, of course, that if there are more rectangles we have to find the areas for, that process will take a much longer time, and how much better will our estimation be if we take more time? So that is our way to make this estimation better, by having more and more rectangles. But we want to try and work out, is there a way we can get a better estimation or a more accurate answer without doing hundreds and hundreds of calculations? And that will be what a lot of the rest of our integration unit will be looking into. So after watching this video, you should be able to examine the area problem and use sums of this form here. Remember, this is basically sum of the area of each of our rectangles to estimate the area underneath the curve.